Going live again. Here we are. Hello, Math222. Hello, Streamlabs bot. Hello. Oh, it's me. People in chats. This is going to be another Chill Maths live stream where we look at some, well, today again, number theory. I'm trying to stick on the same topic and actually get somewhere with this. Maybe. Who knows? Never speak too soon, perhaps. Hello, Murray, who didn't get any pre-roll ads. Very nice. Good to have you with us as well. Hello. I just give people a second because I've gone live bang on 2 o'clock for a change, which, you know, actually here, keeping my appointments, turning up on time. What's going on? Oh, I'm broadcasting quite a lot of jumper and not a lot of... Okay. I roll jumper cam, isn't there? Maybe I'll just do jumper only stream. This could be a new thing. No, maybe not. Let's try center that. There we go. That's terrible, but workable. I'll put it back exactly where it was. Welcome back to this professional stream. Right. I'm very pleased with this jumper. It's still quite a Christmassy jumper, but I'm trying to get away with it. Don't tell anyone, but my Christmas jumper is still in play until I say so. Right. Previously on the stream, we've been learning about continued fractions, which have this notation in this textbook anyway. There's sort of some missing brackets in here, if you like, where there's an open bracket underneath each of these arrows, and brackets all close at the very end. All of them over here, if you like. So sort of 1/2 and a bit. And then the and a bit is expanded in a similar manner. So it's sort of this iterative process. These are good for finding multiplicative inverses of numbers modulo something else, I think. Because I remember last week we got just out of this part down here to see what would happen if you swap the order of the numbers. So this one is 1/2 or 1/2 and a bit, and this one is 1/4 and a bit. And these numbers have an intriguing relationship, which we will get to. Hello, Charlie. Good to see you again. And this feels like a good moment to shout out to Famished Edits, who followed last week while we were live, but then also came along to Maths Club, because I guess they'd followed but forgotten how to find us. They came along to Maths Club at work, online as well, for a reminder of what my Twitch channel is, and then I awkwardly promoted my Twitch channel at work, but I got my own channel name wrong. I got my channel name wrong, so that was no good. But also shout out to ImmyFly12, who followed a couple of days ago, possibly as a result of that conversation. So at the time, hideously awkward. Did it get the follower count up? Maybe. Good. I don't know about the integration B. I'm not really an integration B sort of person. I like integration, but I wouldn't describe myself as quick at integration. If you were doing the integration B, then I hope you have fun with that. Being integratee. Good. Someone showed me some problems once. We did a kind of mini competition where lots of the questions that they gave me were sort of trick questions, I think, where I was supposed to spot that if I did some change, then it would become easy. And I hadn't really got into that mindset. So I did all of them the hard way. But once I worked out there were trick questions, I kind of looking back, I sort of feel like maybe my second integration B experience might be better. Anyway. Oh, it's in tomorrow, is it? What, Monday? Ah, in lecture room 1. This is an Oxford thing, is it? Let me have a look at our room booking calendar. Is that a thing? Room booking calendar. Oh, yeah. UK University Integration B, round 2. It's happening in lecture room 1. Right, good, okay, well, I had no idea. And I'm teaching tomorrow afternoon, so won't be making a return to the integration scene. Teaching some first years about multivariable calculus actually, which is kind of quite similar in style. Anyway, never mind. Okay, where are we going with this? I think if we do this right, I think that today we could actually maybe understand the point. I mean, not like the actual point. We're nowhere near the end of this book, but understand the point of doing continued fraction stuff or doing this kind of this big diagram that we had a couple of weeks ago. In that, if it lets us do inverses in a sensible way, I think that's a good idea. Inverse is modulo n. So where are we down there? Problem sheets. Oh, there's a cute emote, isn't it? Sorry, I'm just watching chat a little bit as well. Herb has discovered that capital R close bracket gives you a sort of Twitch chat bubble, but it's a sad pirate. We've learned how to do sad pirate emoji in Twitch chat only. Capital R for the eye patch. Close bracket. I guess that's happy pirate. Happy pirate emoji. That doesn't look like a happy pirate. Right, okay. Adorable. Right, that's stalling though, isn't it? Because I should be learning about inverses. Right, here we go. Whew. So there's something about reversing the order. Last time we started to understand that there's a product of matrices behind the scenes here. Now, what's that? What's the product of matrices actually do? The matrix product that we were talking about calculates P and Q of the fraction that you would get if you stopped the continued fraction at that point. What is this page? Now this is a page of trying to do iteration stuff, which was great last time, but I'm going to, because it's getting in the way, I'm going to try and remove this page via the secret remove page screen. Oh, look here, it's all the content. It's not showing you all the content though. That's interesting. Oh, I can go to this screen and have a look at the whole. I've got a zoomed out view, which is not displaying on your screen. This is good, isn't it? I could use this for sort of hijinks to. Oh, maybe not. Use this for hijinks. What is going on there? Use this for hijinks to change pages without you knowing where we're going, or skip a page if I don't want to do a page. Okay, good. Right. Well, this is a good look ahead. I've accidentally skipped ahead several pages. Sometimes looking ahead is good for us. It reminds us where we're going and what the point might be. Welcome back to Chill Maths, where it's James, struggling to use a PDF. How do they work? How do I get to where I want to be? Right, here we are. We have all these diagrams, so we have matrices. Now, what are the matrices doing? Right, yes, this is it. In each case, I need to believe that if you store your fractions as if they're a vector, they're coprime, they're in lowest terms, so there's a one-to-one relationship between vectors that look like fractions in lowest terms and actual fractions in lowest terms. That's all fine, no confusion for shared factors, provided we're in lowest terms. And there's some rule about non-zero. You can't divide by zero, so not zero here, or not zero downstairs in your vector. But if you start writing your fractions like that, like vectors, then this operation, goodness me, what are we doing? This operation to go to the next. Wait, are these the tails? No, these are supposed to be the convergence. So there's this operation to get to the next one, which I don't think I understood next time. Oh, it's the mediant. So, okay, so mediant rule, which we've had before, of sort of just doing an operation to add or subtract the numerator or denominator, which I suppose in vector world is this matrix operation. We checked it or something. But it's also something to do with Euclid's algorithm, the way that you calculate these quotients in your continued fraction. I don't think I've understood that step, so I'm scrolling up. Oh my goodness, here are the medians. So that was on the next page, wasn't it? That this combination would be the correct combination. Is that what this is doing? Yeah, that's what this is doing. And it's checking it from the right. So not quite convergence then, but tails? No. I'm interested in what happens if you multiply the first 10 matrices on the left. Oh, your left is over here. If I multiply the first 10 matrices on the left, but the proof that I'm looking at in front of me is talking about what happens when I multiply matrices on the right. Those are related concepts, of course, because I think I know what happens when you multiply all of them. You're supposed to get the whole thing back. And there's a variable stop point. See, it says this value of the tail. And we're supposed to be checking that this is what happens if you do working from the end. So what's going on here? Yeah, this is good. I found a bit from last week that I maybe pretended to understand, or who knows, maybe I really did understand it last week, and now I cannot say it back. So I think this is the boundary of my understanding. There's some matrices going on, there's some operation which looks pretty good, but what's it actually got to do with continued fractions? I think that's where I'm stuck. I intend to be stuck on this for about 5 minutes. So if you wanted to make a cup of tea, if you already understand the link to continued fractions, because we did talk about it last week, this is maybe a good time to make a cup of tea while I mumble to myself about tails. That was supposed to be a trick where I talk but also think about what's going on, but it didn't work because I didn't manage to think. Okay, so tails, joking aside. This tail is supposed to be this last bit of the calculation, so this very last bit where there's no more stuff afterwards in the continued fraction. The very final tail is this one. I'm looking over there, I'm looking over here. And the whole continued fraction is this really big calculation where you do a0 plus 1 over, and then a1 plus 1 over a2 plus 1 over a3 plus 1 over. There's nested brackets throughout that as well, which are quite hard to say out loud. So this one working backwards then is to say that this one, if you working from the bottom of the continued fraction upwards, which I suppose is how you would evaluate it, you would work from this. There's most nested brackets working outwards. So this is how you would evaluate it. Perhaps you'd have that 1 over an, and it really just is 1 over an at the end, and then you would start working them out. So you've got some fractions so far, you've done loads of maths. Time to add on another number here, 1 over that. So this gives you this fraction, uncontroversial, and that is the matrix operation where you sort of move you move S upstairs and you do this weird combination downstairs. So this sort of matrix is relevant because that gives us the next fraction, and it's in lowest terms. So we keep moving, working up. That's how we would evaluate it. So in the end, if this continued fraction really is P over Q, the kind of target fraction thing that we're working with, if it really is that, then after you've done all of these calculations, right to left in that row of matrices that we looked at, you will get to P over Q. That very last one is different. The very last one, the A0 gets added, and it is not 1 over. This sequence starts with an A0 plus rather than a 1 over. I'm trying to point where I'm looking. I know that's slightly annoying because then you look there and there's a red dot in the way. But yeah, 1 over. I saw this research at one point about where mathematicians look. They put eye tracking software on a screen and showed proof with a mistake in it to A, undergraduates, B, research mathematicians, and asked them, can you find the error in this supposed proof of some elementary maths fact? And then they did heat maps of where people were looking over time, maybe. Anyway, the result was that the undergrads would read from top to bottom all the way through, and then started looking at places, whereas the research mathematicians were constantly looking down and up, down and up, down and up, back up, and sort of ending up almost a binary search or something of just like referring backwards and forwards, up and down, jumping around. I wonder if I can find that research. Who did this? Was it Pollard? I'm going to guess Pollard. Math eye tracking research. Oh, this is not going to go well. Okay, maybe not Pollard. It was really good. Okay, the sort of eye tracking thing at least has been done lots of times. There's a big review that I found. Can I find the particular one that I want? Am I going to have to look at all of these? Maybe. Can I remember the authors? No. This is a review, so I found a review with number of studies which is kind of bad news for me, finding the one I want. Yeah, full-size table, please. Ooh. What was it about? No. Ooh, no. It's got complex mathematical text or word problems. Is that the one I saw? Mathematical passing? Maybe it was this. Okay, I've got to go and look at these 12 papers, I think. Oh no, it was one of these. It was one of these. Okay. Can I find this one then? Who knows who I'm allowed to? Ah, there it is. There's this. It was Laura Alcock. That's who I saw do this. Okay, this is in Proceedings 42nd. Time to find out if I have access to this to show you the heat maps. Slightly moving it to my second screen just in case I'm not supposed to show you. Hey! Oh, what's this? Why is it scrolled halfway down? Oh, because I'm supposed to be on page 139. Oh my goodness, this is so difficult. Why is this so difficult? Right, this is it. For the Maths Education Centre, Loughborough. Time to see if I can find those heat maps for Herb. Looking up and down. Right, here we go. 2018, it's been a while. Right, determine whether mathematicians skim read before reading line by line, he says, jumping straight down to methods. To determine whether mathematicians skim read, we recorded mathematicians' eye movements while they read research papers drawn from their own fields. Ah, they're reading research papers. Let's play them already begun. These papers are forwarded to researchers. Okay. They picked different lengths of papers. Interesting. Quiet room, eye tracker, methodology, data. Ooh. Is that just a diagram? This is the type of curve. Skimming. Location. Up and then back down and come back slower. Results. Graphs. What is this? Paragraph number. Time, presumably? No, they're kind of just reading it, aren't they? They're going maybe forwards, backwards a bit here. What is this? What is what? The Mathematician 3 is doing something. Going up and then back to the start and then down to the end again. That's pretty good. Okay. No evidence of skimming in participants' attention while they read entire papers. Okay. Each of these shorter arguments, right? Okay, yeah, go back. That looks a bit more like it. Maybe going forwards and backwards. I'm pointing with my mouse rather than following the curve that they've drawn in the research paper. Okay, discussion. Oh, I thought you gave it to kids as well. This was not the chart I thought it was going to be with kids. Okay, right research. I think correct research is wrong paper. Did you do it? Was it the 2012 one? Where am I looking? Up a bit. No. I just clicked on a link and it did not take me where I thought it would. Oh, this one. Expert, yes, this is it. Right, okay. Second attempt. Okay, right. Expert and novice attempts at reading maths. I just can't get it. I feel like half the time I click on that link, it takes me to where I think it will, and half the time it does not. Expert and novice approaches to reading mathematical proofs. Journal for Research in Maths Education, 2012 paper. I'm having fun. Hello, Derby Derp. First time in chat. Good to see you. We are learning. Well, we were reading some maths, and then I mentioned a research paper about reading maths, and I'm trying to find it. It's Matthew Inglis and Laura Alcock, who I accidentally called Laura. Sorry, Laura. Right. Here we go. Right. So is it the thing I said about they were showing wrong proofs? Disagreements with the extent to which validity. I don't know. Did you do eye tracking in this one? Is that eye tracking? There is eye tracking. Right, let's skip down to the graphs. If you've got any graphs. definitely think I've been to a talk or something where they had graphs. It was great. There's theory in here about how people's attention might work. Here's the method. Let's read the method. Did you give them first year undergrads and 12 academic maths? They were paid £8. £8 for the international audience. £8 is not a lot. Right, good. It's not. That is less than minimum wage for an hour. Maybe it took less than an hour. I don't want people to see that and think, wow, pounds must be worth loads of money. Or maybe I do want people to believe that. After reading each purported proofs, are they right and are they confident? That seems good. Ooh. Are they P1? These mathematicians? No. 6 arguments. Right, so 6 arguments. The mathematicians all agreed that proof 1 was invalid. But the undergrads were split 50-50. There we go. Okay, I'm already interested. Mean total dwell time. How long did you spend looking at formulas or not formulas? Amazing. That's perfect. I love it. Mathematicians don't spend more time looking at text rather than formula, right? Non-formulae. Good, love it. Reading strategy, line of argument. Where are you at? Well, they're kind of working down there, aren't they? I'm sure they showed me a heat map at some point. Maybe just in a talk? No. Mean number of transitions. Where did you go and look next? And the mathematicians spent a lot of time bouncing around between lines 4 and 5 because, spoiler alert, the mistake is between lines 4 and 5. Oh, that's very hard. I didn't find any heat maps. Okay, next attempt. Let's try and find you, first author. Let's click on Google image search. This is probably what I saw. This is, I think, more like the image that I saw. So here's the theorem proof. You can't really read it because of all the dots. That's the eye tracking version for where people were looking. 1, mathematician's eye movements. I'm supposed to compare this with figure 3. So like, the eye movements mostly around this line, going back and forth around this line, but also bouncing up and down. Versus figure 3. Can I get to figure 3? No, why figure 2? Figure 3. This is what the mathematician was like when they were reading text at the start. So they had the eye trackers on while they were reading the instructions. Brilliant. Okay. That's the formulas chart that we just saw. And then figure 6. More back and forth movement. Okay, so maybe their point is that I'm going back and forth. People reread the line that's wrong. Okay. What's this then? Oh, who knows? Right, okay. Charts might be out there. Oh yes, Lara Alcock did How to Study for a Maths Degree, and 2 more books that I've got actually. I've got the Abstract Algebra book and I've got the Analysis book. Lara Alcock kind of wrote the How Should First Year Students Learn Analysis. Is sort of in some sense solved because Lara's done loads of work on this. It is not really the case that this is how people are still making mistakes that would be fixed if they just read Lara's book. It's also a book that students can read, so I'm going to promote it now. It's called How to Think About Analysis. I recommend this for people who are at uni learning about analysis. Good. Right, okay. Enough maths education research for a second. I said I'd spend 5 minutes thinking about a thing, and I've spent at least 15 minutes not thinking about it. Welcome to the stream. If you're new here, and hello Debbie Derp. Yeah, if you're new here, we are trying to learn maths, but quite slowly. I've been looking at number theory for about 3 of these now in a row. Can't really tell you what I've learned. Matrices can be used for. You can use matrices for working out continued fractions, or at least calculating the tails of your continued fractions? I learned that 15 minutes ago. Right. Yeah, it might not be too late. Also, there is a lot of maths that I learned, well, I thought I learnt it 15 years ago. That was probably my peak for thinking I'm learning maths. And then a good amount of that maths, it turns out that my understanding was quite patchy. And part of the joy, I think, of being graduate and looking back and not doing this for a degree is that I can decide which bits I want to understand better, and I can do it much, much slower. Hey, I've invented a part-time study. Here we are. Right, okay. So we're calculating tails of continued fractions, which is what you would work out, not if you want an approximation to a number, but if you want to work out the fraction again, to convert your continued fraction back into a fraction, you've forgotten what fraction it is, and you need to calculate 1 over 2 plus 1 over 3 plus 1 over 4. Well, if you want to work out what fraction that is, you really need to start at this end and start calculating. So why am I thinking about approximates then? Approximates would be if you went from the left and you said, well, it's about 1/2. Is that good enough? Not really. Well, it's about 1 over 2 1/3. Is that good enough? Not really. A bit better, but not really good enough. Okay. I'd like to think about approximates, but maybe not. When you're working out these numbers, so we've got about 4 things to relate together. We've got the big chain of matrices. We've got the continued fraction expression, just evaluating the continued fraction expression. We've got the big diagrams with all the curved lines that bounce around. If you've just joined, I'll show you in a second. And we've also got ideas about Euclid's algorithm being used to calculate the numbers in the continued fraction. I suppose it's that last one I want to think about briefly. That when you're calculating these numbers AI, you start from the left when you're calculating them, because kind of Euclid's algorithm is a sort of an approximation in a way, right? You have like 13 over 30. That's about 0. Or said differently, do I want to do it the other way up? Not really. So you have 13 is sort of 0 times 30 plus 13, and then you look at your leftover stuff to say that this is about 2 times 13 plus a little bit more, so 26 plus 4, and then you say that 13 is 3 times 4 plus 1, and then finally you say that 4, so you keep working with these either the numbers you started with or the remainder. So you take these two, 13 and 4, 4 and 1. 4 is 4 times 1. And then this column here of quotients, 0 out the front, plus 1 over 2 plus 1 over 3 plus 1 over 4, close, close, close brackets. That's the continued fraction, these quotients in that column there. I think I've got red. Yep, I have some colours. The colours don't display until my device is really strange. Does it now work in red, does it? Oh, it now draws in red. That's an improvement. Oh, did it do something weird there? Yes, it draws in dark red and then appears in red. Oh my goodness, okay. The device I'm using is pretty odd. Okay. Yeah, it's sort of like here. And then pop afterwards. It used to be much worse. It used to show in black and then switch. Oh, blue these days. Kind of the same thing. Okay. I have this very strange tablet device that's in black and white, but has the ability to produce colours that I can't see on the device. It's a bit like having colour blindness for the device itself. Navy pink has made the thing here. Have we said navy green before on the stream? We used the phrase navy green, or did I say that somewhere else? I think navy green, you know what colour I mean. Right. The navy, famous darkener of pigments of all hues. Right. Okay, I said navy green as a stupid thing that I said somewhere else. Good to know. What am I doing? What am I doing? So I sort of convinced myself that 13 over 30 really does come if you work from this end, combine things together. Yeah, it's not at all clear from the chain of matrices. It's not at all clear why multiplying from the left would give me approximants or anything that's closely related to the fraction. I don't think I've got any sense of the distance between fractions yet. The book's called Topology of Numbers, so I think distance between numbers might be the point. Haven't got there yet. Right, so the long chain of matrices is kind of maybe just an element of this proof to demonstrate that when you do the mediant rule, you generate the same things. I mean, working from left, but in the end, you get the same thing as if you combine from the right from your continued fraction. So if you believe in continued fractions and you believe in using the median rule to get somewhere, you will get to the same place. Okay, right, I think I'm almost there. The matrices are maybe just an element of this proof. I don't know if we're going to see a lot of them going forwards. Anyway, right, interesting fact. We are now here. I think that was my 5 minutes. That's taken us to 2:30. Reversing the order of the numbers, which I think is completely mad, because what's that got to do with anything? Leaves the denominator unchanged, because the matrices, here we go, transpose the matrices, and you get something like this, with no initial integer a0. The transpose of a product is something to do with the transpose of each of these. Yeah, that's just true in general. In this product, the individual matrices on the left side of the equation are symmetric, so they're unaffected. So it's just reversing the order of the factors. So reversing the order, right, I see. So reversing the order gives you the fraction with reverse things, because the transpose is the same. But on the right, we've said that this was calculating all along in a kind of little Fibonacci matrix kind of way. It's generating these numbers, which when you do your transpose, you get this. That's totally different, isn't it? What? Oh, it gives you, yeah, but it's got the same Qn at the end, but it's Qn minus 1 instead of Pn upstairs. So it's a different fraction. Different fraction that you get by doing it in that order, but same denominator. And there'll be some nice relationship, right? Yeah, here we go. Fairly simple relationship between, I would like to know about Pn Qn minus 1, because they're taking it in turns here to be the numerator of, I'm reading this last thing as the fraction. I think that's how this works. The fractions are the columns of the matrix, and you need the previous 2. Do you need the previous 2? Or maybe, yeah, because you're going to do some median rule stuff. Anyway, whatever. Okay, so the product of these things, Pn Qn minus 1, one of these is 7, one of them is 13. It's congruent to 1 mod the denominator, 1 mod Qn. It's quite nice. In the general case, the product of the numerators is Pn Q minus 1. This is congruent to minus 1. So the m plus 1 modulo the denominator Qn. Ooh, okay. So it might be an inverse, or it might be up to a minus sign, but that's okay. And it's because determinant is multiplicative. The determinant of a product is the product of the determinants. That is quite a good fact. So then, in a way, a bit like, you can do this for the Fibonacci numbers. I suppose I keep saying like the Fibonacci numbers because if you set all of the ANs to 1, then this generates Fibonacci numbers. We just look at the determinant and then it falls out. And there was this, so I should have spotted, okay. And that sort of came out of the blue, but I should have spotted that if you want these two, tell me something about the product of these two up to a multiple of those two, or up to a multiple of that. I should have thought what multiple of that is easy to talk about. Oh, the determinant contains a multiple of that. So, okay, maybe I'll spot that next time. Up to a multiple of Qn. And they will have the determinant minus 1. They do, that's brilliant. Okay, which implies that Pn Qn minus 1 is congruent to minus 1 to the n plus 1 mod Qn. I can probably turn that into a Fibonacci fact, right? where for the Fibonacci numbers, if you set, this will be 1 over 5 or something, but if you set A0 to 0 and then have 1 downstairs, so you get the product of these matrices, the same matrix again and again and again, I think that gives Fibonacci numbers. I'm doing it again because I think this is a good way to get a handle on what's going on. So this will be, so the 0, 1 pulls out the second column, and the 1, 1 adds together the previous columns. So if you multiply that by 0, 1 again, the 0, 1 pulls out the second column, and the 1, 1 adds the columns. So you get this rather nice sort of Fibonacci pattern coming along. And I suppose the determinant fact is going to say something nice about Fibonacci numbers, which I feel like I might have seen before, which is going to be something like fn minus 2 minus fn minus 1 squared is minus 1 to the power of, I've definitely seen this before. So this is n of them to give me 1, 2, 3, depends how you count, but something like this. 5 times 2 take away 3 times 3. So 5, I believe that to be 1, 2, 3, 1, 2, 3, 4, maybe I want this. 5, 1, 1, 2, 3, 5. 5 is the 5th Fibonacci number, I think, if you start from 1, 1. Maybe I call those F0 and F1, in which case I don't want this plus 1. Because then it's F4. Parity. This is Fm plus. This is Fn. So is this. Yeah, cool, whatever. It's got a name, which Maths2222 in chat knows. I didn't know, so I'm looking it up just to check. Yeah. Yeah. I got the minus and 1 signs. I got the minus 1 signs in the end. Yeah, good. Okay. Catalan's identity generalizes this. And that's been a step question. And I'm getting too far onto familiar ground, I think. Right, good. Which I suppose means that Fn and Fn minus 2 are maybe plus minus are multiplicative. One of either this or minus this inverses mod Fn minus 1. It's a bit weird, but it's not nothing. Okay, we're going to look at the exercises and maybe not do the exercises. Oh, maybe we should. Maybe we should. That question 2 looks pretty good. I don't want to evaluate these. I don't want to calculate continued fractions for these. I don't want to draw lots of triangles corresponding to those, although it would help me verify that I can remember which way up the triangles go. Question 2 looks good though. We've hit the exercises. It's good times, good times. Continued fraction of 38 over 83. Yeah, sequence of equations involving only integers. This is the sort of thing I was doing in the margin just before, wasn't it? The first go around gives you 0 for A0. And then the next one down, is that giving me 2 38s? 2 38s are 76. Plus, what do we have left over there? 76 and another 7, I think. 60, 76. Yep. And then 38 is 5 times 7 plus 3. Oh my goodness. 7 is 2 times 3 plus 1. And 3 is, right here, 3 is 3 times 1. So I believe that this 38 over 83 is 1 over 2 plus 1 over 5, 2, I didn't leave space, 3. These columns, 2, 5, 2, 3. Didn't leave space for that, did I? Okay. For the same number, compute the associated strip of triangles, groups, and fans, including labelling verses. I just can't be bothered. I don't really have space. You can take the continued fraction, reverse the order of the numbers AI to get a continued fraction. Okay, so I can reverse things. So how do I want to lay this out? I kind of want to do 0, 3, 2, 5, 2, and then work backwards to work out what these numbers are. So if I reverse my continued fraction, I can now work upwards to work out what number this is. It's always times It's always times 1 at the end. Oh, I'm working with... Yeah. I'm trying to work with things that are co-prime. So their highest common factor is supposed to be 1, which means it appears here as well. So I'm supposed to work backwards by filling in the quotients like this, 22, 24, and then 24 and 11. So 60, 72, and 11 is, 83. Right. That's blindsided me. That's 83 again. Oh, yeah, all right, okay. Same denominator. Same denominator. Shouldn't have blindsided me. It's the fact that they have the same denominator. So there's 107. So I think this is 83. Before we had 38 over 83. No, not. It can't be 0 times 83. What am I doing? These steps make sense to me. Sorry, 0 times 83. I think I just wrote down 0 times 83 plus 24 and claimed it was 100 and something, but in fact it's 24. 24. What is the relationship between 24 over 83 and 38 over 83? Is it something like 24 times 38 is, and there are 1, 2, 3, 4 of these. So perhaps it's going to be one more than a multiple of 83. Let's find out. I didn't back myself to multiply 24 and 83 on stream together. Times 38, and not even do the right ones. 912. So do I think 911 is a multiple of 83? No. Is it -1? Is 913 a multiple of 83? Yes. Okay, it was -1. -1. There was a -1 there all along the chat. Was there a factor of n+1? Oh, it's n+1. n+1. Up by 1. Okay. The 24 times 38 is 1 less than a multiple of 83. Okay. Find equations in terms of P minus 1 Q. I think I'm alright. Each of the n terms of AI is equal to 2. Oh, like this. Okay. I think I'm alright. A rectangle with the questions are all 2, so it's going to be. Anyway, never mind. A rectangle with sides like this. It's the sort of square root 2 thing, isn't it? That Maths 2 made me do last time. It's all the 2s, like your username. Right. Okay. A rectangle with sides like this can be partitioned. This is an activity that we make people do on summer schools. You do some division, so you have a long side here, large number, that is 48, and a small number, which is 13, and you start putting squares in from this end, and you can fit 3 of them in before you run out of space. You're doing Euclid's algorithm, the kind of division, and then you have this kind of leftover amount of space, which comes from 48, take away 3 lots of 13. 3 lots of 13 is 39, so this leftover space has length 9, and then this is supposed to be filling up squares, so in this direction next. And if you keep doing that, then you build this kind of pattern. They're not spiraling in this one, they are going into the right hand corner, lower right hand corner. So you fit 1 square in because 13 is 9 plus 4, and then 9 is 2 lots 4. You can keep going iteratively downwards. That's this way to visualize it. The number of layers in Euclid's algorithm is equal to the number of numbers in the continued fraction. Yes, possibly out by 1, depending on whether you count a 0 at the front, and possibly out by 1, depending on, are you counting? Yeah. But the quotients that you do in Euclid's algorithm, the quotients that you find in Euclid's algorithm are precisely the numbers that you put in the continued fraction. For a rational number, that terminates. So you're good. You've got your entire continued fraction. For the irrational numbers we were talking about last week, we're going to keep going forever. So equally endless, or something. But yes, the lines of Euclid's algorithm is one of the four things that I'm trying to piece together. I've seen kind of the same maths in different angles being introduced by different people. One approach to doing this kind of stuff is to just do Euclid's algorithm first. One approach is to do continued fractions first, which you calculate by doing Euclid's algorithm, but you secret. Or you do something like this, where it's just kind of Euclid's algorithm in disguise. And then this textbook has shown us a big circle diagram and doing this kind of median rule thing for narrowing in on your fraction, which, you know, I've seen so many versions of this where we're just certain that it's the same thing. And in fact, we've done some proof that if you write out the quotients or whatever we're calling these numbers, that it evaluates to the same thing as the continued fraction. So it's the same. So can you do Euclid's algorithm with matrices? I think that's what was going on about 15 pages ago. Let's see if we can find it. So not last week, but the time before, which was actually 3 weeks ago. About there in the book. Oh no, that was the intro. Okay, I've lost it now and forgot to make a note of what page I was on. So welcome back to How Do PDFs Work. So there's all this preview stuff. Was it in the preview? No, there was a big there's a big section with matrices in here somewhere. Yeah, we were proving something. What were we doing? This, right. This stuff. Right, so this stuff where you're reducing things. We had some matrix and we did some reduction on it by always do subtracting the column with the smaller second entry from the column with the larger second entry, so that these two entries remain positive. We stop the process when they become equal. So I think this is secretly Euclid's algorithm. I can't quite tell what numbers it's operating on. Possibly 8 and 19. Possibly 8 and 19. This is storing things in matrices. Is it really matrix operations? Hard to say. But I suppose the point here was we were using very basic matrices so that we could talk about the determinant. Just doing this kind of subtraction each time. So here we've got 8 and 19. You start taking 8s away from the 19s. It's taking away 8s plural from the 19. So you're kind of writing 19 as well. Come on, it's like 2 lots of 8 plus 3. This is where you get 3 over here. And then doing it the other way around to look at here and just start subtracting from this one. That's a bit like saying, well, 8 is 2 times 3 plus remainder 2. So it's going to happen down here. It takes us 2 steps to get there, but then we get there to 2, and then you're doing this bit at the end, which looks like the Fibonacci numbers to me. And these numbers are co-prime, so we'll end up with down here ones. We know they're co-prime because the determinant of this matrix is, I think, selected to be 1 or minus 1, which means if there were a common factor between here, it would definitely appear in the determinant, because it would be in both the AD bit and it would be in the BC bit. So then, interesting question perhaps to try and link these things together a bit more. And maybe if I did the exercises, then I'd know this already. What's going on with the numerators up here, right? What are they doing? And possibly they're doing something to do with quotients, but not really sure. So maybe this is naive. Maybe it's not on 8 and 19. Maybe it's on 7 and 19. Maybe it's the same thing. Huh. I definitely thought I could read that as 8 and 19. What do we get? A smaller column with the larger second entry. Stretching the column with the smallest second entry. Oh no, it is definitely on these, isn't it? But no, we keep going. So it's this 7. We're just doing something sensible, right? Subtracting 3s from this 7 until we can't subtract more 3s. Subtracting. Well, I guess it's not now. It's not, the next step is not to do Euclid's algorithm on 3 and 1. So I was going to say something very wishy-washy to say that it's also doing Euclid's algorithm up here, but it's really not. So doing Euclid's algorithm over here. What do I mean? No, not at all. Not even slightly. Okay, so I think this is Euclid's algorithm on 8 and 19, but I'm not sure. I don't know what else is going on. Oh, this is the extended at Euclid's algorithm thing, right? Where you also keep track of numbers such that am minus bn is 1 or maybe minus 1. I'm not certain how these determinants have worked out, but sort of 1 or minus 1. If you can solve that problem, then you can solve the zoo as well. So some people do this extended Euclid's algorithm thing. I think it's this, where you keep track of those numbers upstairs as well. Yeah, okay. So you can do something like Euclid's algorithm, storing numbers in matrices, if you then write down very carefully what the matrix operations are. You can multiply by the inverse of the later matrix to get it though, can't you? Ooh, what can I get? 0, 1, 1, minus 1. Oh, are you claiming that's the inverse? I'm very thick, sorry. Yeah, does that take me forwards or backwards? What does that do? What am I multiplying? Matrix from later. Oh. Yeah. What is going on? It's a hard question, isn't it? What is going on? What is going on? Anyway. Do you think all of these are the same thing? I mean, the clue is that they're all in the same textbook. It'd be weird if they were unrelated facts. Oh, I said I'd show you someone some diagrams. We have these diagrams of the number line. They're pretty weird. They've got these circles on. Wait, no, that's the forward circles, which I sort of skipped. Diagrams. Right, okay. Yes, that's... Oh, I see you've picked that matrix to kind of do the subtraction. Do you have to sometimes stop and subtract the other way around? Sometimes you want to subtract from the left column and sometimes you want to subtract from the right column. Maybe you've got to do both. I'm not sure. Okay, back in. I'm not quite ready for proposition 2.2. I was looking at some infinite continued fractions. Excellent. We're just on these exercises. Right, write down the product. Associated 2, 3, 4, 5. No thanks, I'm fine. Oh, illustrate the proof of theorem 2.1. Oh, I do sort of care about that. But it's just going to make me do the matrix multiplication? Not sure about this. Not sure about this. Fine, okay. It's not hard, so let's just do it. And then a cup of tea, maybe. Motivate yourself with this easy trick. 0, 1 brings out the second column. 1, 3 gives me 3. 1 and 6 is 7. And then they want me to multiply that by 4, which gives me second column. 1, 4 gives me 1 and 12 is 13. 2 and 28 gives me 30. I know these fractions. 3, 7, 13, 30. 0, 1, 1, 5 gives me 0, 1 picks out the second column. 1, 5 gives me one of these, 5 of those, 50, 65, 68, 157. Feels unlikely, but here we are. 157. Okay, maybe it's 13, 30, 68, 157 in that lower right corner. 4 matrices. Oh, I did those. Related to the edges of the zigzag path. These are the conversions. And okay, so they let me evaluate the continued fraction from the left by using this kind of median rule to say as you go through. So these 4 things that I was working out along the way. Is it time to think about triangles? Maybe it's time to think about triangles. So the zigzag path in the strip of triangles. I think, do I start down here? Do something like 1, 0. Am I supposed to start at 1, 0? And then what's up here? 1, 1. Add it twice. Because the thing is 2. To get to 3, 2, maybe? Am I supposed to do it like that? How did these triangles work? Is it 3, 2 over there? Yes, these ones. Those ones. Where have they gone? There they are. So for a small number, 1, 0. Oh, I suppose to put 0, 1 down here and start my continued fraction like this. I've used the sort for numbers larger than 1, maybe? Not sure. Yeah, so I'm supposed to put 0, 1 down here and do it that way up. Good. Median rule, very tricky. Right, okay. We go again. 1, 0, 0, 1. 2, 1, 2. 2 is 1 plus 1. Just going to check once more. It's 1, 0 upstairs, 0, 1 downstairs. 1, 0 upstairs, 0, 1 downstairs. And then start doing your continued fractions. Let's go. So median rule twice. Apply this fraction twice, gives me 1 over 2. And then 1 to 3. Apply this 3 times, gives me 3 of these. 7, 3 over 7. 3 over 7 looks a bit like the thing I had before. Down here somewhere I had a 3, 7. There it is, 1, 2, 3, 7. So the matrix still feels like it's representing the line between these fractions rather than the fractions themselves. Because then I'm going to take 3, 7 and add it on 5 times, and I'm doing the same calculations, right? 5 3s and 1 is 16. 5 7s and 2 is 37. And I now realise that I think I've got some calculations wrong back here. Oh, it was 4 next. It's 2, 3, 4. So I want 4 3s and 1, which is 13. And 4 7s and 2, which is 30. Good. Okay. And then about 5 of these later, I'm going to get my last fraction. So solid line to take me to, finally, think of this maybe as a vector or maybe it's a fraction. Over here, 5 of these, so 65 and 3 is 68, and 30 downstairs, 157. So the median rule definitely does the same thing as the matrices. The edges of the zigzag path, right? So these solid edges give me the fractions, and the lines kind of represent. So we've got matrices like this, and that's kind of a line between these, is how I'm thinking of it. Anyway, right, so calculate these from the right-hand side. Okay, then more matrix multiplication, and relate these to the successive fractions you get when you do the calculation from the right. I don't think I really want to, but they're the same calculations both times. So does that convince me that they end up being the same? Kind of, I suppose. Same matrices multiplied in 2 different directions give you the same thing. Fair enough, it's not my favourite proof ever, but hey. Okay. Oh my goodness, look, here it is. It's the 8-7 thing we were just thinking about. For 7 over 19. Oh, right, I was wrong. It really was the column or something. What's this 8 doing? There's some interchangeability going on, I think. 719, but where's this 3, 8 come from? Wait, it exists so that the matrix has determinant 1 or minus 1. So if you want to do the continued fraction of 719, this is only a viable method if you can think of a matrix which has 719 over here and some numbers in here. So if you already know some numbers, then that with determinant 1 or minus 1, it's 30, 57, take away 56, amazing stuff. Compare this with the sequence. Right, okay, so continued fraction of 7 over 19 is something like 19 is 2 times 7 plus 5. Here we go. That is a good sign that we're on the right lines, by the way, that we went back and looked at something. It was also there. 2, 1, 2, 2. 2, 1, 2, 2. So 7 over 19, I'm going to do this down here. Equals 1 over 2 plus 1 over 1 plus 1 over 2 plus 1 over 2. So then the matrix representation for 719 or something like that is something like 0. So these matrices I was just multiplying with the 0 on the left. Ah, it's that t sign. I think it's t sign. Yeah, it's the 0 on the top left. We're getting there. The matrix representing that thing is supposed to be something like this. So here's a string of matrices. And reading from the right, if you multiply these together, then you're doing exactly the calculations to recompute the number 7 over 19. Well, you're not, you're calculating a matrix, but the number 17 over 19 will be on the right. So I think this, what do I want to do? I want to pull out the right hand column. Maybe? So if I pull out the right hand column, I should get 7 over 19. The left hand column is interesting. But okay, so these are steps of Euclid's algorithm running on the numbers 7 and 19. But also they're the steps of Euclid's algorithm running on 8 and 19. And that's not super surprising because 8 and 19 are up to minus signs, multiplicative inverses mod 19. Because 56 is pretty close to a multiple of 19, plus or minus 1. It's slightly less than a multiple of 19. There are 4 matrices here. N plus 1 is odd. Determinant has a minus sign each time. My goodness. Right. Multiplying from the left, though. Multiplying from the left. Okay, so these transformations are the things with the repeated subtraction that we just looked back for proposition 1.1. Repeated subtraction steps. The repeated subtraction is like running Euclid's algorithm from the left to get the sequence 2, 1, 2, 2. But if you recombine it, you get the matrices, right? If you recombine it, you get the matrix. And you will get... Yeah, okay, so if you don't know this matrix, you can multiply the matrices to get the numbers 3 and 8, which give you numbers A times D and B times C, such that AD minus BC is plus or minus 1. So then up to minus signs, you've got a combination AN plus BN. So then the left-hand side gives you this thing, the left-hand column of the matrix. Okay, so I thought it was running on 8 and 19, and in a sense it was. I think what we've learned maybe is that if M and N are multiplicative inverses, mod, I hate those letters, right, okay, if P and Q are multiplicative inverses, mod N, then P over N, Q over N have same number of steps in Euclid's algorithm. And better than that, the steps are just the reverse or something, or up to a minus sign, which, up to a minus sign? Oh, that minus sign's annoying. Okay, but up to a minus sign. Good, right, that seems like a good place for a cup of tea. I think it took an hour, but I think we've got a better idea about how the matrices do the calculations that you would do when you're calculating to simplify a continuous fraction. Or you could say that they're doing some combination by median rule, which appears in our Fairy sequence. If you care about approximants, then the Fairy sequence, this kind of F-A-R-E-Y, Fairy sequence of numbers, gives you approximants. Multiplying to the left is going to give us approximants. Not obvious yet why they're close, but it's going to give us approximants. There's some topology there, maybe, to say that they're kind of nested within each other, so that they end up being really close. But multiplying from the right gives us like literally the number. So this checks that you have a representation of your continuous fraction. It's going to get to the number. And then you have this information for what if you read it from the left, and that gives you the path. It's just a matrix. The matrix with the matrix, I do like this matrix decomposition actually. So this matrix decomposition with 0, 1, 1 payload, some sequence of numbers in these matrices. You can use that to make any coprime pair in the right column. You know what the determinant is going to be, which is a good fact. And if you multiply from the left, we're going to see that you get some interesting sequence. So this sequence of matrices exists for any fraction, if you like, any fraction in lowest terms like this. Tiny bit of projective geometry going on. Never mind. So this sequence of matrices exists for any fraction. I've previously only been thinking really about multiplying from the right, but I now sort of see that multiplying from the left gives you a different way of looking at the fraction or something. I went very weirdly philosophical at the end there. Right, cool. I'm going to run a quick ad and make a cup of tea. This is also a chance for you at home to make a cup of tea if you've just joined us. We're going on a quick ad break as long as it takes my kettle to boil. We'll see you back in a couple of minutes for infinite continued fractions. The fun sort. Bah, they're all fun. Okay, right, good. Ad break. So I click this, and this, and this. I'm back. Oh, right, yes. Good ads. 3 different ads for the government, car insurance, Ionos, and Army. Always gets an ad for the Army. Hasn't worked yet, as far as I know. Herb has not yet purchased an Army. Don't know, maybe you're really into Warhammer. Oh, hi, Phobos Stream. Welcome to the stream. Good to see you. Yes. What has happened there? Twitch has done something funny. I know I always say this when I come back from an ad break, but Twitch has done something funny. It's always surprising me. Welcome back. Right, yes, here we are. Welcome back to the show. What are we doing? Look, that's the best one I've seen yet. This kind of picture, nice clean picture of this kind of way that you bounce between these numbers as we calculate them. Very good. Today's tea is Yorkshire. Almost always is. tried other teas are available. And we have the cat mug. Right, that made me feel like I was sponsored by tea or mugs or both. Yes. I've realised for infinite continued fractions, waiting for the kettle to boil, which is an important moment in the live stream, chill maths, is to take a break, boil the kettle, make a cup of tea, and surprisingly often, while making a cup of tea, is when I realise something about what's going on. Infinite continued fractions aren't going to have a right end. I've just been congratulating myself on understanding things, multiply from the left or you multiply from the right, and now the next section is going to be a big long list of matrices with no right end. So, what? Okay, we will see. We should make a routine that controls the kettle. I mean, we have tea time. Tea time sort of controls the kettle, not directly. I'm not connecting my kettle to the... Oh, we could have a little cam for it. A little kettle cam. And you could send requests over it for... Yeah, to play along. That seems safe and responsible. Yeah, kettle cam. It would fit just in next to the Chill Maths logo. Squash it up and put the kettle cam in there. People could use channel points to fire electrical appliances in my house. Yes, Brill. I just got one of those. The enormous bag of Yorkshire tea bags. I just got one of those too. Great. It's a great purchase, but then you need to find somewhere to store it, and as Herb says, the size of a large baby. Good. No, Mario's out of points. Right. We've been running this thing which it's sort of somewhere in between a channel points redemption versus a kind of normal ritual for the stream. I think I've sort of been trained. I've been trained that 3 o'clock is when tea is. So we're going to find out whether that just keeps happening. At which point, if it just happens anyway, then that's sort of quite weird in some sense for all of the point spending. Mary has been the kind of modern day equivalent of an ancient religious rite to herald the rising sun. Mary does it every morning to herald the rising sun, and then the sun rises, and then Mary runs out of channel points, and we find out whether the sun still comes up or not. Next week, I think we find out whether 3 o'clock tea time is still a thing or not. So they get Pavloved. Get Pavloved. Alright, get Pavloved, right? Brill, right. I'm just a sort of Tamagotchi. Like, I learn maths, and then you press the button to give it tea. Right, here we are. Here's the Fibonacci numbers making yet another guest appearance in this sequence of events. Yes, the famous Fibonacci sequence, good. Here it is in the upper half plane diagram, bouncing around. Fibonacci. Keeps changing direction every time. Fibonacci time. I'm trying to speedrun the Fibonacci section here because we have already talked about this. Each one's shorter. Ooh, right, hang on. Here's a description. After the initial vertical edge, this path consists of an infinite sequence of semicircles. Yes. Each one shorter than the preceding one. I think this is the one scaled to be the actual positions of the numbers, so the jump is smaller because each one's smaller. Well, it can't be larger than the previous one because it can't go further than the previous jump. It's got to land somewhere within the previous jump. Okay, each one shorter. I've decided now, uncontroversial. Showing common endpoint. The left endpoints of the semicircles are an increasing sequence of numbers which have to be approaching a next page. Approaching a certain limiting value x. X has to be finite, certainly less than each of the right endpoints. So these convergence. Yep. Similarly, the right endpoint's coming down, and the left endpoint's coming in, the right endpoint's coming in. Question which analysis people who have done a Gaussian analysis will see the trap. The trap is to say, aha, this one's coming in, this one's coming in. They're going to get to the same point because they could leave a gap. But in this particular case, we've got a sequence coming up and a sequence coming down. The infinite sequence of semicircles would approaching to the semicircle from x to y. You'd see this kind of xy kind of limiting semicircle, I suppose. Above this semicircle, there will be an infinite number of semicircles, all the semicircles in the infinite sequence. Yes. Between x and y, there would have to be a rational number, p over q. This proof is brilliant. This is great. Wow, maybe it's kind of the standard proof, but you say semicircles quite a lot of times. Anyway, never mind. There's a rational number in between p over q. So above p over q, there'll be an infinite number of semicircles and has an infinite number of triangles. We know there are only finitely many. We saw that. I'm not certain we proved it, but okay, they're the ones in the continued fraction for p over q. Oh, you can actually reach p over q. Yeah, and the lines can't cross. Yeah, okay, that's pretty convincing. Fibonacci stream. Fibonacci stream. I think most of the chill math stream comes down to Fibonacci numbers in the end. Yeah, okay, so there's some sort of... You might worry that this sequence of semicircles is messing around, doing infinitely much stuff, but without closing the gap between some numbers x and y. And this proof is brilliant. This proof says, consider the sequence of semicircles for p over q, some rational number in the middle, is going to come down like a kind of lightning bolt straight into p over q, no messing around. Because, okay, Fibonacci number is doing something weird, p over q, it's going to have some finite sequence of semicircles going there, and these lines are not allowed to cross. So, determinant reasons, I think, way back when. So that kind of comes down like a lightning bolt through the rainbow, and hits p over q. I think that's also going to be a proof that this limiting thing. Ooh, maybe I'm speaking too much here, but maybe it's going to prove that it's irrational. If the limiting point is rational, then this dancing around would be from the left limit and the right limit would have that property that it would cross over. So I think it has to be irrational. I think this is a proof that any infinite continued fraction is rational, which is kind of obvious because any rational number has a finite continued fraction. So never mind. Right. We're covering continued fractions. What about discontinued fractions? That is, I believe, an original joke on continued fractions. That is rather good. That is original, I think. Oh, did you see it in the chat box? I wasn't looking at chat. That's Megalomorph. A+. Right. Phobos, this textbook divides by 0 quite a lot. I don't know if you spotted it in this diagram, but this textbook has a just alarming amount of this and this. There is some sort of continuation, completion going on to allow us to write that. I'm not saying it's allowed, because the other thing this textbook is doing quite a lot is that this textbook is kind of switching quite freely between fractions and vectors with those two numbers in. And in vectors, there's no problem with having 0 downstairs. And in fractions, that kind of is. But the book's switching quite freely between those, relying quite heavily on things being written in lowest common terms and all of the vectors being co-prime numbers. It's a thing. Let's have a quick look at the fairy diagram again, because I want to point at infinity in it. Where's that going to be? Back there. No, I've missed. But quick look at the fairy diagram. There it is. Oh, it's gone. That's the rescaled one, which I don't love anyway. Fairy diagram. Whoa, in all of its majesty. It's a little bit like projecting the real number line onto a circle. It's not quite that, there's some distortion, but it's almost projecting the real number line on the right, projecting it onto the circle. So sort of 0 in the middle, negative numbers down here, project. Infinity would then naturally be this kind of very far away point. So it sort of wraps around here. That is kind of what the book's up to. Good. It's made of quarter circles, and I believe an asteroid is not quite quarter circles, but I think it's very close. Is asteroids powers of 2/3? I've been here before. An asteroid is circle in a circle, but it's not quite quarter circles. It's 2 powers of 2/3. Envelope of ellipses. Right. Okay. I'm going to go back now. Fairy diagram. Oh, if I hold down the button, I get a preview. That's good to know. Welcome back to How to Use PDFs, a Twitch live stream that's informative. You learn a tiny bit of maths and you learn quite a bit that I don't know what I'm doing. Can I drag this? Yes. Oh, amazing. So I can choose where to drop it. Oh, what great power. 4 circles. Oh no, okay, but it's quite slow to load. That looks quite good. Let's drop there. Oh, it didn't even work. Sometimes I feel like this live stream works as a really good advert for these tablet things, and sometimes really not. Unique limit. Oh yeah, here we are. It's proof work. Oh, you it's well, yeah, okay. Converting to a real number. Unique limit. It's also going to be irrational. Is that what's going to happen next? Yeah, fine, okay. Not quite. This is the converse of the thing I said. Maybe. Nope, it's the same thing as the thing I said. It's about irrational numbers. Good. It can't be the converse and the double converse. The double converse is the same. Right. How are we doing? Okay. Yeah, prove the lower end point is not a vertex since x is irrational. Move downwards, cross a sequence of triangles. Okay, so imagine straight in, and it's going to be this finite number of triangles above. It's kind of weird then. In this upper half plane model with the circles, kind of semicircles, it means that above any rational point there's a finite number of lines, but above any irrational point there's an infinite number of lines. That's mad. Where do the infinitely many lines come from? That's a brilliant fact. The fact is something like, take two fractions in lowest terms, write them as a matrix. If the matrix has determinant plus or minus 1, draw a line between those two fractions. A nice semicircle curving through the upper half plane. Above any rational point, there are finitely many lines like that. Above any irrational point, there are infinitely many lines. That's so good. Where did the lines go? Above root 2, loads of lines. Above 1.4, nah, not that many. So where did they all come from? They came from all of the weird fractions in between 1.4 and root 2, and lots of the semicircles are really tiny. But you can have, so these lines then corresponding to, the lines are joined up by this determinant 1 or minus 1 thing. So you can find arbitrary, it must be the case that you can find arbitrary fractions that are arbitrarily close to root 2, both of them, such that this determinant is 1 or minus 1. And that's probably with massive numbers corresponding to, which is going to help us solve equations, I think. The lines are, because the lines are the ones on a Fairy diagram, and they correspond to the continued fractions of what's going on of these things. Because the lines above unfold, the lines that pass above unfold to the median rule stuff with the upwards and downwards triangles that we've been looking at. It's that but distorted around. The lines above you are the ones for, well, you know, if your continued fraction has 1 over 3 plus, there are kind of 3 lines. And then there's, if you look at your next number, and there are 5 kind of coming the other way, and then 3 under that. Maybe if the next one's also 3, and then maybe your next number in your continued fraction is 7, so there's sort of 7 on the other side. Why did I pick 7? I was doing so well demonstrating that with my fingers, and then I picked a number bigger than... Maths, very hard. Okay, and I think this is what this is describing as well. Except for an irrational number. Yes, good, okay. I want to find those numbers, I think. These ones near root 2. Sorry, their ratio is approximately root 2. And you can do something funny with combinations of numbers in this sequence to give -1 or +1 approximations to root 2. And you do that by doing the continued fraction. You do the continued fraction of root 2, and this will say that the approximate... It's starting to sound a bit untrue, isn't it? But no, it's still true. It's still true, isn't it? So find the approximate to root... Find the convergence to root 2, sorry. Find the convergence, multiply the matrices from left, because that's all you can do for root 2. Multiply the matrices from left, and you'll get a sequence of these fractions that are very close to root 2, but with kind of determinant for the fractions. Yeah. I don't think we're there yet, but we're getting quite close to having large integers that solve an equation. And I think it's a linear equation at the moment, but I could imagine that this textbook is going to tell us how to do other things as well. I mean, there was an advert at the start that this book includes a proof of which primes can be written as the sum of two squares. I think there's an ad that's in the book. The values that the quadratic form x squared plus y squared can take. Okay, right. Okay, I'm almost sold on the fairy diagram sort of thing. I think I prefer the upper half plane model. The circle thing, maybe the upper half plane. I'm a bit more sold. The semicircles corresponds to the things you calculate. The things you calculate when you're working out the continued fraction. If you do subtraction only, no fun Euclid's algorithm division, just boring subtraction each time, you get a bunch of lines. Okay. For uniqueness, this set of triangles is unique, so the strip is unique. Yeah, that is quite elegant. Only one path that starts at, left and right turns alternately, starting with a left turn. Each one turn must be to the left. A1 larger than 0, what is going on here? A1 over A0 over 1. Okay, if you have A0 bigger than 0 or something? Oh well. Also left, right. Okay, we've got some idea about what this picture looks like in general. Maybe that's the topology. The triangles therefore cover the whole upper half plane, which we didn't really know before. They are triangles, they've got semicircle edges, but they've got 3 sides, so if they're triangles. Lies either in the interior of some triangle on a common edge between each triangles. Vertical line, if x is an integer, then it's very good. If, the line L will then be contained in the strip of triangles corresponding to continued fraction for x. Finite if it's rational, infinite if it's irrational. Either case, that point will be included in the kind of bit of a slice through the diagram. That's mad. Okay, right, good. This book has now won, I think, permission to tell me some facts about continued fractions, which I've always found quite difficult, but welcome to have a go. Here we go. Patterns in continued fractions. You're running Euclid's algorithm, you get into a loop. What does that tell you? Famous loops include being stuck on the number 1, which gives you something to do with the golden ratio, being stuck on the number 2, which gives you something to do with root 2. Other numbers are available. 2 natural questions. Hello Fletcher CC, welcome to chat. It's Chill Math Stream. We're learning about continued fractions. And I've got a mug of tea. If you want to play along, we're learning about continued fractions for irrational numbers. If you want to play along, you could get a cup of tea. Okay, Megalomorph. I was thinking about this. I was trying to remember this. This looks good. Yeah, people are always telling me this. I think this textbook is going to tell me this as well. gives me x squared minus y squared is 1. You see, that looks like my discriminant fact. But I've been imagining that as 2 successive approximants. So, what am I doing? I don't have a thing squared. Thing squared. Yeah. How am I going to get my x squared and my y squared? How do they relate to these numbers in my fractions? It's not just x over y, is it? Or maybe it is. You know, we have that kind of Cassini identity thing for the previous one, but that's relating together Pn and Qn minus 1. So I can't immediately see how... I agree, it is true that the continued fraction for root 2, you take the convergence, and they do give you solutions for x squared minus y squared is 1, but I can't quite see why. I will get there. I will get there, I think. Oh, there's a 2 in there as well. Maybe that's what's going on. Yeah. You could use sigma notation. I don't know if I love this notation with the arrow. So the arrow is supposed to include a kind of open left bracket. Divide symbol. It's kind of this instead of divide by left bracket, which I promised to close right at the very end. I'm not sure I love that as a notation. But it is very, in line. Other people write just some notation. So long as you're storing these numbers, people might write sort of square bracket stuff. I assume that this book is going to at some point change these numerators. I don't know why, or how, or when, but they've chosen to use a notation which includes the numerators. So I assume that that's going to come into play at some point. I don't know anything about those. If they're roughly square root 2, then I agree it will give me roughly. It sort of roughly works. I think it would be exactly 1. I'm imagining something like... well, should we go down that rabbit hole very quickly? Let's go down that rabbit hole very quickly. So I need the continued fraction for root 2. And because this stream is chill but not lazy, we're supposed to actually calculate this. So this is 1 over root 2 minus 1. And then root 2 minus 1 is like 0. Nope. Yeah, here's a true fact for a change. 1 plus, and there's some stuff. And I need to write this stuff as 1 over something. Well, it's 1 over root 2 minus 1. That's a kind of tautology that it's 1 over root 2 minus 1. So let's try and simplify this fraction by rationalizing the denominator. That's right, that thing that you learned from school, right? Rationalize the denominator. Difference of 2 squares. Root 2 plus 1. You learn this in school or something, and everyone says, oh, what's the point of rationalizing the denominator? Here we go. It's a natural thing. It's good. Give this root 2 over 1. So I can write something like this. Root 2 plus 1 over 3. And then this number down here, I've messed up, I think, because that's really small. 1 over root 2 minus 1, root 2 plus 1, it's 2 minus 1. 2 take away 1 is 1. Difference 2 squares, make a really good point about maths education and learning things. Not even there. N equals 2, 1/3 plus x over n. What does that do? I don't know what that does. Okay, this is about 2.4, so I should write 1 over 1 plus 2 plus. Maybe the stream is a little bit lazy. 1 plus, and then root 2, so then it repeats. Laziness rewarded. So if I want some convergence, then I can do something like truncate this after. Let's go down to this bit here and truncate here. So my first approximations are things like 3 over 2, which is not great, but we're trying. And then there's 4/3 is the next one. And then I get So then if I include this half, I get 3 over 2, which is flipped to 2/3, which you add the 2 and you get 8/3. You flip it, you get 3/8. You add the 1, you get 11/8. So my observation is that if you do a kind of determinant thing on these, 9 take away 8 is 1, 32 take away 33 is -1. That's kind of this determinant factor that we've had before. But yeah. Oh, should it just be 2s all the way down? What am I working out? Yeah, mine are too small, aren't they? Maybe they're too small. Fine, I'll be lazy and I'll use Wolfram Alpha. Oh, it is 2s all the way down. Oh, I messed up. By the way, Wolfram Alpha has some notation for this, which I've never seen outside of Wolfram Alpha, which is this kind of large K. So goodness knows how this works. Look, maybe if you like Sigma notation, you'll also like big K notation. It is 2s all the way down. Okay, so my continued fractions are incorrect. Back in we go. Where did I go wrong? 1 plus 2. So there's a 2 in here. Plus root 2 minus 1, and then it repeats. So then it's 2s all the way down. Okay, good. Right, so if I truncate, I get 3 over 2, or that's 2.5, 5 over 2, 2/5. 2/5 plus the 1 is 1 and 2/5. We've discovered the approximation 1.4, 7/5. And my observation is that 15 take away 14 is 1. Yeah, neat how that still works, even though the continued fractions changed. And if I go one step further, then I get this 5 over 2. Well, I should flip it. Instead of adding the 1, I should add 2 to get 12 over 5. Flip it, 5/12. 17 over 12. That's a moderately famous approximation for root 2. 1.4 is famous. 84 minus 85 is -1. But then the thing people in chat are telling me is that like 17 squared take away 2 times 12 squared is actually 1, which is an exciting solution to the equation x squared minus 2y squared is 1, which I really can't see at the moment. I can't see how you'd get that fact. What is that in terms of the matrix? Oh, good question. Sounded really clever. Oh, no idea what I'm talking about. It is 1, yeah, but sorry, I should have calculated it slowly for a dramatic reveal. 289, take away 2 lots of 144. 288, 289, 288. Really does give 1. These numbers really do. You can keep calculating them. Continue fraction, get solutions. Something that Megalomorph told us in chat just now. But I really can't see why at the moment that works. So this looks like a determinant, but with a 2 in there. Why is there 2 in there? What does it want? I mean, I could do the maths. It's not hard to work out. This thing that we're doing each time is the operations are kind of so the operations are add 1, because this was plus 1 at the end, add 1 to get to 29 over 12, flip it to get 12 over 29, and then add 1 to get 41 over 29 or something. I don't actually believe that. Maybe I should believe it. This solution is telling me something like 41 squared take away 2 times 29 squared is... Oh, that's -1. Okay, so there is an alternating plus -1. Okay, maybe we're onto something. Maybe we can understand this in terms of what we've just done so far, because there's a -1 in there. And this really looks a lot like the Cassini identity, right? This is a square thing minus some previous things. Can I write this as some sort of matrix operation? So maybe it's true that might write that as a matrix operation and then just tell you what the determinant of the matrix is and be done. Maybe. Maybe not. Annoying. Yeah, no, I can't quite see it. I can't quite see it. How is this? Oh, I guess I could write down the kind of algebra of what you're doing, right? That you have P over Q, maybe Pn and Qn, and the continued fraction thing is telling us to evaluate. So I've been describing this as, whereas +1 at the end, actually if you want to go another step, you just need to add another 1, and then flip it, and then add 1 again. So this is kind of Pn plus Qn, flip it, and then add another 1, so add that to the Qn that is upstairs. To do something like this. So just quick check, 17 and 2 lots of 12. It's more calculation than I was expecting. 24, 30, 41, and downstairs add the numbers 29. So you get this kind of operation, this pair of operations, which is multiplication by the matrix 1, 2. If you think about this as a vector, then the steps that we're doing to work out the next approximation thing is to multiply by this matrix, which we haven't seen yet. That hasn't turned up so far, I think. But if you think of this as like vector Pn Qn, I guess again this book switches between fractions and vectors quite a lot. Then what we're doing to get to this vector, if you read that as a vector, which I'm not sure that you should, upstairs. Oh, do I mean this matrix? I might have messed up. Maybe I don't mean this matrix. I'm going to write it out and then fix it. Pn and 2qns. I do mean this matrix. The approximates are called convergence. I keep saying approximants. I know it's convergence, but yes. Sorry. In my head, they approximate. That's how I remember. They also converge. So maybe I should remember that instead. Yes, convergence. Good. So because it's applying this, then what? Now what? So it's just doing powers of that matrix. So I still sort of want to calculate the determinant of that matrix, but maybe I'll restrain myself from calculating powers of that matrix. Oh, this is going to be a sort of... so then our fact is going to be something like... It's not quite in the right place. It's not quite in the right place, but it's almost like you multiply this on the left by Pn Qn by another vector, transpose, or maybe the wrong way around. Multiplying this on the left by Pn Qn, and on the one hand, what's that going to do? So the observation is that this thing squared minus 2 times that thing squared. Sort of quadratic form thing. It's 1 or minus 1. So can I interpret that as the determinant of something? Not really. Maybe? Not really. Trying quite hard. I could put another one in. Yeah, but what's the determinant of the matrix? That gives us the alternating plus or minus signs, but what's the determinant actually doing? In terms of the numbers P and Q. Oh no, not quite. Almost there, almost there. You're calculating some numbers, right? So you start, where do you start? Way down here, you start with like 1 over 2 or something. 1 over 2 is itself. Two over 1 or something. 4 take away 3 is 1. 15 take away, no, I don't love that. I don't see how the determinant is related to squares of the numbers here. And also, the thing I'm currently looking at is a vector. So it's only got these things in once. So maybe the thing I'm supposed to be considering is something like this matrix and do the determinant of this. So the determinant of this is kind of the quantity that I want. It's got a very similar shape to this matrix, hasn't it? It's got 1s and 2s in it. How does that matrix transform? How do the QNs get transformed? Not quite in the right way. Maybe I put the 2 over here instead. Right, how does this matrix transform? If I multiply it on the left by 1, 2, 1, 1 times this, then I get Pn plus 4Qn, which is nothing. Put the 2 back over here. On the left, I will get exactly the right stuff. Pn plus 1, Qn plus 1. And on the right, I will get 2Qn plus 2Pn, which is 2Qn plus 1. Yes. And 2Qn plus Pn. Okay, it's really hidden. It's buried down here. That's Pn plus 1. That's the next one. Okay, this matrix. Right, fix it, tidy it up. We got there. I think we got there, chat. This matrix. Find the determinant of that one, because that one also transforms. If you multiply on the left by this 1, 2, 1, 1 matrix, then that calculates the next convergent. Nailed the wording. That calculates the next convergent, but it's determinant of that matrix, which gives you the difference of the squares thing. And possibly I'm missing a trick. Possibly I can do even better by writing that as the matrix again. Is it the same matrix? What's going on? Almost the same matrix applied to something really simple, like PnQn. Almost. Right, good. Okay. Yeah. There's a matrix proof of the Cassini identity. Although the nice thing about that is that when you see the proof, the Fibonacci numbers are in the matrix twice. And adapting that step, I want a matrix that contains these numbers twice. That was the hard bit. I put PnQn on the left, and then I had to work out what to write over here, and thought maybe I should write it underneath or over there. The hard bit of the Cassini proof is thinking about which matrix to write down. Good, right, I'm actually pleased. That does work. That transforms in the correct way. Can I tidy it up at all? I think RFL. So generalize? Yeah, RFL in chat. Reflexivity. We wanted a thing, we got the thing. Hey. General Pell equation, right? What's going on? If you replace number 2 with D, where do you write D minus 1? Some of those 1s are secretly D minus 1, aren't they? So you're working out your continued fraction from the left. You're working out these convergents. There's some medians rule for how you get to the next one, which is not quite what I've written down, is it? I thought we had this before. The medians. I thought it had A's upstairs and downstairs. That's not what's going on here. So I must have misunderstood that before. I must have misunderstood that before. Maybe. I've only got this number in. That's kind of my quotient. My I sometimes call them quotients. I sometimes call them numbers in the continued fraction. Good. Yeah. Okay. Megalomorph, thanks for prompting me that this is related to Pell equations. I think that's an interesting place to look. Just want to go back and think about, so this is supposed to be a convergent for the continued fraction, and that adding rule is not the mediant rule that I thought we'd been using. Am I just wrong? no, because I'm not doing an additional step on the right, I'm doing an additional step on the left. And on the left end of this row of matrices, which is becoming my preferred way to think of these, this like row of matrices for 0, 1, 1, A1 or whatever they are, on the left things are a bit different. And adding an extra matrix to the left does something different. In general, I need to remove the A0 part. Remove the A0 part. Add in another one of, this is a repeating pattern one. Repeating pattern, so I do need to know, if I want to do this in general, I need to know about the continued fractions for square root of d, for other values of d. Right, which is what this section is all about. We've successfully got to the point where we've worked backwards to the point where we are in the book, because that's what these are, I think. Periodic continued fractions. The sum matrix. So then that's going to be an extra kind of matrix transformation? Sure, so then the continued fraction, the periodic bit will give you some matrix transformation, like this one. Some matrix transformation that you can do. This is the product, by the way, of removing this 1 plus on the front. There was some matrix that put it there. And then putting another 2 in the sequence of these things. And then putting the 1 plus back on the end. So I guess it is, I'm going to get these the wrong way round. Something like 1, 1, 0, 1, 1. And down there, and then an inverse matrix for that one. Is this the inverse? Maybe this is the inverse. Thinking. That's not the inverse. How do you do inverse matrices? A and D, switch places, you divide by the determinant, which is -1. So 0, 1, and these switch places. Is that the inverse? 1, 0, 2, 0, no. Oh, you divide by, you put this -1 in. 0, 1, no, 1, 0. Inverse matrices in a small space, out loud. Not going well. Inverse of this matrix, come on, James. Yeah. Oh, math 2 to 2 to 2, I think this one's coming up in a couple of pages. Yeah, whatever. This matrix, and then this should give me 1, 2, 1, 1. Anyway, complete this calculation later. Not interesting TV. Yes, okay. Special class of rational numbers, patterns. Includes the case the whole continued fraction is periodic. For example, so what is this? 5, 7, 3, 5, 7. Oh, 3, 5, 7. Eventually periodic versus ones that are just periodic straight away. Write a bar over the block of terms. Can be written, is that the end of the page? Nope. Can be written as like this, repeating for the bar for the repeating bit. Simple algebraic manipulations, as we now illustrate by finding the value of this continued fraction like this. Oh, Fibonacci, here we go, quadratic equation, good. Fibonacci is back on stream. Good. Yeah, we know it's positive, right, good. What about this one? With a 3 at the front as well. So we want the repeating part, which is some number on the end. If we're evaluating the tail, so we can evaluate the tail for a repeating one because we have some rule. So this is going to repeat. There's an x. All of this bit is also equal to x. This is a session that I do for a summer school, where you have not just continued fractions, but other operations that repeat, and the trick is to spot the repeating bit. The point of the session is to demonstrate that this doesn't always work, but let's not worry about that right now. It doesn't always make sense. What are we going to do here then? So it's going to rearrange this, very nice. Okay, we're going to get some sort of, are these in general algebraic expressions, or are they always quadratic expressions? I think they might always be quadratic expressions. And I think this is going to now prove that. I said I'd give the book some leeway to prove this. Let's read it. How the continued fraction for an irrational number. Yeah, okay. Yeah, or you can just run Euclid from the top, can't you? And just approximate stuff. Yes. Yes. Okay. Good. Decreasing denominators. Yeah. This looks a lot like Euclid. So much so that I'm not going to look at it and just assume that when I said you can run Euclid, you can just do it. Okay. So it's going to say the convergence all checks out. No. Ooh. Subtle points. Define these being add them, evaluating them right to left. Evaluating them is to add the A naught. Can we evaluate them right end since there is no right end? Hooray. Evaluating them left to right as the limit of this sequence of convergence. Adding a fixed number A naught to each term of convergence sequence numbers adds the limit. Okay, right, fine. Good. Okay. This is... Ooh. Huh. Okay, yeah. Great for finite continued fractions. You're supposed to keep passing to the limit, right? Value becomes the last step of inverting. One of the reciprocal, the convergence for the... Okay, limits. limits. Yeah, good. Okay. Reciprocal convergence, good. Okay, fine. If in doubt, go from the left. Think about limits of sequences. Check that it works for those. Here, the procedure works. For root 2. Okay, good. Exactly the same. We just did this earlier on the stream. So no, we root 2 plus 1. I did it wrong, but I had a go. Continue, get this, and it's the thing that Maths222 said in chat. Check this by finding the value of continued fractions the same way. Good, get this convergence. And then down here, we are now speed reading. We've learnt that mathematicians tend to skim read, so we will also skim read. That will make us a mathematician, right? Converses are always true. Root 3 has some interesting pattern like this. Oh, brilliant. Okay, so we've now had two examples where we looked at a repeating pattern and got a root of a quadratic, and then we looked at simple roots of quadratics and got repeating patterns. It is true in general that for every positive integer n that is not a square, the continued fraction for root n, the thing we're looking for the Pell equation reason, because we have successfully, I think maybe for the first time, worked out, with a lot of help from chat, we have worked out where this is going, worked backwards from there enough that we're interested to know the answer to the question, and then flip through a couple of pages to find we're almost at that question. We have a series of right limits of what we would like to know, and a series of left limits of things that we're reading, and a proof that there will be no gap between these things in the end. This has a repeating form. We're going to see why now. Here we go. The length of the period can be large, even for fairly small values of n. Okay, just for now, they're just saying it's large. Okay. For example, root 46 is wow. Who knows? The last term is always... Oh no, here we go. Right, here are some fun facts. These are not in my sequence of things I wanted to know, really. Last term is always twice the first term. A0, oh my goodness. The last term is omitted. The previous terms in the period form. A palindrome, excuse me. A palindrome, 13112621131. Palindrome. This is section 42, which is miles away. No megalomorphia, you're motivating what we're doing. I was thinking some of the Pell equation stuff, couldn't see how to make it work, and then because someone in chat wanted to, that's why we tried to make the connection. That's why we're now motivated. These two properties follow from certain symmetry properties of the triangles in the fairy diagram. That sounds really hard. Is this a repeating pattern? Put them on the way in. How many triangles you get? You can read it forwards and backwards. That's not something I can obviously see. Is that like inversion? Do 1 over and you'll get the same. Do you invert the fairy diagram? Weirder things have been done. Here's Lagrange's theorem. The irrational numbers whose continued fractions are eventually periodic are exactly the same So that was of this form. Ah, is that the roots of quadratics? A and B are rational. There's another way to write this. Wait, is that just... That does sound like the same thing as what I said, but that's... I'm thinking the quadratic formula... Oh, I said roots of quadratics, and that includes loads of stuff, doesn't it? I should say roots of quadratics with rational coefficients. There are many Lagrange's theorems. Let's see if I can find the one I'm looking for. Lagrange's function for a periodic continued function. So this is the other way to write continued fractions, which is huge, isn't it? Look at this. Maybe I'm supposed to just read this Wikipedia page, right? Maybe I could learn about Minkowski's question mark function. Unusual fractal properties. Let's not go there. Doesn't sound good. Sometimes we go down a Wikipedia rabbit hole on this stream. It is currently 4 o'clock. A quadratic irrational number. Right, good. Yes. Right. I should have said irrational in there as well, because it's an infinite continued fraction. Real root of the quadratic equation. By the quadratic formula. Good proof. They look like this. P, Q, and D are integers, so they've put these things over a common integer. D is not a perfect square, because then it would be a rational number, but it could be square free, so you could pull this thing out. Okay, so I prefer the way the textbook is writing this, to be honest. That Wikipedia phrase is closer to what I was thinking, but this is closer to perhaps to what I should be thinking. Okay, and then here it is on screen as well. This is one of those times that it's on screen. They're roots of quadratic equations with integer coefficients. I said rational coefficients. I should multiply through by the least common multiple of the denominators. Right, easier half is you have a quadratic irrational. Proved by showing the method we used for the ones we did works in general. Or geometric version of the procedure in the next chapter. Wait until then. Quadratics eventually periodic. Not all apparent if any examples root 2 and root 3. Chapters 4 and 5. Oh my goodness, right, okay. Actual proof is in chapters 4 and 5. So we have some road ahead of us, I think. Okay. More efficient methods of computing continued fraction for quadratic irrational and for computing the value of eventually periodic infinite continued fraction. Nice. Okay. And then I think this might end a section, so I'm going to have a quick look at it. But this might end a section just to have a look at other ones. E has got a nice continued fraction. Goodness me. Of course it does. Successive even numbers. Even simpler. Things built from E. Oh gosh, that is very nice. Oh, that's too nice. Oh dear. Good old Euler. And Lambert. Oh no, Lambert, what have you done? No. What have you done, Lambert? Continued fraction for this? Okay, fine. Big in the 18th century. Continued fractions. Pi has got this brilliant one with 292. Some approximations to pi. This one's really good. We should all learn this one. 355 over 113. It's too large to have a day named after it. But it's a surprisingly good approximation. Yeah, there is a formula for pi over 4 or something involving normal fractions like this. I think that's just an observation that the odd numbers turn up in lots of places, but what do I know? So, yeah. Yes, the 292 is fantastic, which is why we should learn this one. Nothing wrong with these ones, but this one is especially good. I think sort of even by the standards of a continued fraction approximation. Let's put it in the calculator, just have a look at how brilliant it is. So 355 divided by 113. 3.141592, and then slightly off, but it gets the 14159.3-ish. It's perfect. 1, 2, 3, 4, 5, 6 decimal places. So it's accurate to like 1 part in a million, and the denominator is only 100-ish, so it's surprisingly good. Yeah, start with the denominator, 113355. If you prefer, you're learning a fraction that approximates 1 over pi. Hey, good old pi. So the one's surprisingly good. This book hasn't yet told us that the convergence for continued fractions are very good in any sense. There is a fact like that. Sort of, what is it? There's a fact like among the convergence for continued fractions are all of the numbers that are all of the ones that are closer than 1 over q. No. I can't remember the fact. Something like they're close like q squared instead of close like 1 over q. Okay. Immediately preceding a large term with continued fraction always gives an especially good approximation because, well, in terms of the semicircles, you get loads of semicircles. So they'll be really near one of the endpoints. But in terms of continued fractions, it's because now you're going to do 1 over 292, and 1 over 292 is small. Plus further corrections, but maybe so I'm brushing things under the carpet, but maybe the semicircles make that clearer. Oh, I knew that. Look, here it is. They've put things in the numerators. There you go. That's a classic reason, I think, to put things in the numerators, because you would like to show someone this nice fact about pi. That one is pretty spooky. Good old pi. Right. Oh, now we're going to do approximations now. It's continued fractions of the numerator one that have the best properties. So that's it. We've discovered the one and only reason why they're writing out the ones in the numerators is to show you this party trick. Discovered by Euler. And I think no other reason worth it, I'd say. Look, it's great. It's worth writing all of these ones out here instead of writing the kind of square bracket notation. Maybe it's a bit easier to read. And it's a bit closer to the big stack of fractions, so I think it's got other things going for it. But you do have to write out a lot of ones, just so that occasionally you can do this. Yeah, the best rational approximation thing. I tried to say it out loud, failed. It's coming up now, look. Megalomorph is 2 for 2 on what's this book going to do next. There they are. Oh, there's the one for root 2. One's for root 2. No? Yes. 1 plus root 2 or something. Okay, fine. These are pretty good. And what are we doing? Ooh, there's the 1 over q squared fact. Right, good. We're going to stop here, I think. I'm going to put a bookmark just here. I'm going to have a quick look at what's coming up next week. Forward circles. I should maybe go back and learn forward circles. Action required. Think about how good these convergents really are. It's within 1 over q squared. That's pretty good. That 355 over 113 is within kind of about like 100, 1 over 100 squared of pi, which is better than you might expect. If you choose the best possible approximation of pi with denominator, some sort of fact, denominator at most 113, that's the best one you can do, or something. You can improve it by a factor of 2. Okay. This looks like the sort of thing Megalomorph's thinking of. Oh my goodness, with circle geometry to prove it. I think I am going to need to learn what those forward circles are. Because look, here they are, all being tangent to each other and stuff. Right, and then doubly infinite. Oh my goodness, no, don't do that. Doubly infinite strips? That's not a continued fraction at all. Where's that going? And there's a path that's going to cross a lot of lines. Single infinite fan. Right, okay. Where is this? Oh, paths like this from alpha to beta. Okay. What's going on there? Infinite in both directions. Okay, I don't see what that's going for. Connecting two irrational numbers, alpha and beta. 2 roots of a quadratic equation or something. Okay. And then there's some exercises. And then we are going to get on to it. To start off with linear Diophantine equations. But I reckon this book is going to have to give us some quadratic ones at some point. Determinant minus 1. Chi-prime numbers, you can do the zoo sort of stuff. Diophantine equation like that. What else is coming up in this book? 5 function, all good. Okay. Oh, triples. What? I wasn't paying attention. And now there's 3 things. Chinese remainder theorem. solve a series of congruences. Possibly by doing n things at once. Oh, okay, good stuff. We've got a whole section on that to look forward to. Euler 5 function. An example with a quadratic Diophantine equation. Okay, now we're getting there, because now we're going to get things like solutions to this. Has a solution one average positive integer n, but does not have an actual integer solution. Here's an example. Obviously it has no integer solutions because those squares will give you large numbers. It does have rational solutions like this. Solution what n for certain values of n in the following way. Okay. And build your solution. Special case of the general problem of solving quadratic equations. Central theme of the book starting in chapter 4. Okay, so it feels like there's some more stuff, digression of rational points and quadratic curves, some more stuff that we've got to learn that still seems a little bit familiar, although this is 3D, so that's quite exciting. Things like Chinese remainder theorem, which people have taught me before. But once we get there, hint user very, it's time for some symmetries in chapter 3. So if we can get here at some point in the next month or two, then we get to start thinking about, then we're going to start thinking about all possible symmetries of the fairy diagram and what they tell us. Okay, seems good. Yes, phi is the worst. Sorry, Megalomorph. Another shout for continued fraction things. Phi is hard to approximate. Okay, right, I should not try and read this now. So I'm going to bring it back to reality. That was page 76 or something, so bringing it back to reality in here somewhere. We're doing quite well. We've got some ideas about infinite continued fractions. We've got this result stated that you have the ones that repeat are the irrational numbers of the form a plus b root n, a, b, and n integers. Oh, sorry, n being rational. And then we've got some other facts about continued fractions. So we've got some things in here about how well they approximate to come, how well they approximate, and then go back and do some Chinese remainder stuff, linear Diophantine equations, before we get to do symmetries. And it is the symmetries which have been advertised as being how we're going to prove that for root 46 there's a kind of palindromic pattern and a number that's twice A0 in there. Okay, good. If the symmetries of the fairy plane help us prove stuff, then sign me up. I'm already liking the kind of nested, the fact that they're nested, the semicircles kind of nested within each other has been helpful so far already to show that these things converge, the lines can't cross. Good stuff. Right. Thanks for joining in. Thanks for your directions, of course. Thanks for keeping everything chill. I've got to wait 2 minutes for Mary to do something, possibly to save up channel points. So it's a new experimental bit of the live stream called Building Channel Points with Mary. What am I going to do in between? I think I want to find. I've got 5-10 minutes. I think I want to find the. I'm sure I've seen a heat map for that research. I think it's just more of the research by Matthew Inglis and Lara Alcock. Maybe I'm misremembering it as a heat map when actually it was these points pointing at things. Sorry, this data. I'm still looking at this again. I've got it on my second screen. Let's put it in chat. Right, can I see the full text of this? So this is 2015. It's a later article looking at investigating and improving undergraduate proof comprehension. So, that's Lara and Mark Hodds and Matthew Inglis and Somali Roy. Okay, so I guess I should look at some sort of like Google Scholar page for some of these people, if I can find them. found Matthew Inglis. There we go. Finding a chart that I saw years ago. Good, right. So public access. Ooh, 23 articles available. Nice. So I think we had a quick look at this one. That's the 2012 paper. I haven't looked at some of these. There's the modelling paper from 2007. Oh, is that Charlie Gilmore? Anyway. Self-explanation training. Self-explanation is a kind of thing I've heard about as a hot topic. The idea is that you, as well as reading, you try and explain it to yourself. That's really simplistic, right? I've just read out the name of the event, but the kind of elements that we're doing along the side, like in the margins, and rephrasing things and trying to find examples and trying to work out what the point is. I sort of think all of these things are kind of related concepts. What on earth is the approximate number system? Anyway, never mind. I'm not finding. Show me more eye tracker. Show me more eye tracker things. That's what chat liked. Good, right, okay. Ooh, that's 2 to 2. Amazing at finding stuff. There's a video with a heat map. That will be perfect. That is what I want. Heat maps, it does have the heat maps. Yes, well done, Math 2 to 2. Heat map. RFL. RFL. Good. Rubber duck debugging. Oh, I think that is what I'm talking about. I think self-explanation is more than that, and I should read the papers. Maybe that's my homework. There's definitely a tendency with maths that just reading it, it's not. It's tempting, but almost doesn't help much. Well done, Math 2. That's a good find. I've seen this talk. I think. And you can now see, spoilers, but you can now see where the problem might be in this proof. It's like literally, there it is. Hardly looking underneath the talk, right? Because they got here and then there's a bit of bounce. This is other parts that are important. I don't know. Are these the undergrads or are these the saccades? That's the word for it. That's the word for it. Bouncing up and down. Mean number of between lines saccades per proof. How much are you jumping between lines? Distance. No, distance 1. I don't know. I don't know what a saccade is. Okay. I thought you were just doing that more. Good. Right. Cool. Okay. Well done for finding that. Thank you. Ah, great. There's half an hour, so that's my homework, I guess. Right. I'm ending the stream, to use a phrase that Herb gave me for how do you end a stream? You just announce down the barrel of the camera, I'm ending the stream. Thanks for watching. See you next week.